So hello everyone. Today we have Jingxiang Wu from Oxford with us, who will tell us about three manifolds and MTCs. Jingxiang, take it away.
All right, thanks. So thank you all for coming. So yeah, I'd like to talk about a recent work I did with Federico and Sakura. We put out very recently, and I will also mention some upcoming work. So before I start off, I like to tell you where we are headed. The rough idea is going to tell you about a correspondence we proposed between MTC on one side and the geometry on the other side. So MTC is going to look like a bunch of factors multiplied together by this kind of product. And the object I will, in this category, I will call anions. On the other side, it's a three manifold labeled by a bunch of coprime integers, pi over qi, and together with the choice of group. So for simplicity, I will restrict to SLNC in this talk. It should be straightforward to generalize to other setup, but this is the setup we understand the best at the moment. On the geometry side, the object we are interested in is certain type of flat connections on M3. This whole construction is heavily inspired by a series of papers from 2020 and to last year. I highly suggest you to read those papers. They are really interesting. So I'd like to spend a few slides just to give you a very quick background of all those notions that described in this slide. On the geometry side, well, starting is the special type of free manifold called Seifert manifold. This is very easy to describe. It's a 3D manifold that's a circle bundle over a punctured Riemann surface of genus G with n punctures. To construct this manifold, you just take a Riemann surface and you remove a few small disks, and then if you glue, if you fill in little disks, you get the original Riemann surface times S1, the trivial vibration back. However, if you fill in the disk given by this type of combination, where this M is a cycle around this little disk and L is a cycle around the S1, you get a very non-trivial manifold. Another way to say this is you start from a trivial vibration and you take out some solid torus and glue it back in with some bend twist. So this is a quite simple-minded construction of three manifolds, but it turns out it's quite powerful. Many three manifolds are Seifert, and there's a famous theorem from there was a conjecture, but now it's a theorem from Thurston that there are 8 types of geometries in 3D, and 6 of them are Seifert. And today we'll only look at when the base manifold is a sphere, so when the genus is 0. It will be interesting to generalize to higher genus. Let me know if you have any questions. So on the other side, we are studying MTCs. This is a very well-developed area. It's super relevant to physics, and it has a very heavy machinery as well. Fortunately, we don't need much of the technology today. So basically, it's the mathematical language to describe the TQFT in 3D. And to describe it, the simplest way to do that is to use a fusion algebra, which describes the fusion of anions. And you also need to tell me how the anions are breeding with each other, which is S matrix, and how anions twist, which is the T matrix, together with the central charge. Unfortunately, this is not the full description it's been understood recently, you also need F and R symbol to fully uniquely specify MTC. But that's harder to describe. So there's a whole bunch of consistency relation for all those data to satisfy in order for a category to be a modular tensor category. In particular, if we drop the requirements that S matrix is modular, you get something called a pre-modular category. In other words, if you have a pre-modular category and you further require the S matrix is non-degenerate, you get MTC. So the objects, so the category that's of interest today is constructed as follows. So each individual factor is called the category of finite dimensional modules of quantum groups. So if you don't know this, it's okay, because we don't need the the technology from quantum groups. The only few facts that's relevant to us today is how the objects are labeled. It's essentially labeled by the weight in the F1 L-well curve. So you may recognize this is the same as Chen-Salmon theory. And indeed, if you choose Q here to be 1, you get exactly the Chen-Salmon theory of SUN at level P minus N. Now, if you choose other Q, that just give you different type of root of unity, and this you still have the same fusion ring, but the details are a little bit different. For example, S matrix, P matrix, and alpha R symbols could be different. And it's known that.
Quick question.
Yeah.
For other Qs, are these just like Galois conjugates of Q equals 1, or is it more complicated?
Some of them are, but in general, it's not.
I see. Thank you.
Yeah. So this category is known to be pre-modular, but it's not necessarily modular. For example, for Q equals to 1, sorry. For Q equals to 1, it coincided with Chen-Salmon's, which is modular, but in general, it could be non-modular. Now, the final ingredient we need to understand this proposal is this product. So to my knowledge, this product was first defined in the paper by Cui, Chiu, and Wang in 2021. The construction is very natural and simple. So if suppose you have a category and it's graded by a abelian group, let's call it A, and this is your category. Physically speaking, this is just a one-form symmetry. So you have a MTC describing a 3D TQFT, and A is your one-form symmetry. So suppose you have 2 MTCs. Now, sorry, if you have 2 pre-modular categories, they are both graded by A, you can define a product that takes tensor product of each individual graded component. So this is a subcategory of the usual Deligne product, and it's known to be pre-modular. And of course, by construction, this is again an A-graded. However, this operation is very mysterious, because one way to see this is that it does not preserve modularity. It could send modular categories to non-modular categories, and it could turn non-modular category into modular categories. So even if you like you don't care about Seifert manifold and all those business, I think it's already a very interesting question in itself, just to understand this operation better. Like, what would it mean physically? And it turns out this product is very powerful in our proposal, and like it gave us lots of mileage in understanding new MTCs. So now here's the proposal. Right. So I've explained the minimal background for those two sides, and so before I dive deeper into the proposal, like how it actually works and why we believe they correspond to each other, let me give you some motivations. Like, please interrupt me at any time if you have any questions. So yeah, so this proposal looks nice because it relates to very different things. But why we are starting this? First of all, the motivation from MTC side. As a physicist, this is very important. It's known to describe the math part of the 3D TQFT. So if you ever want to understand what happens to a low energy of a three-dimensional theory, you need to understand what are MTCs and what are the space of MTCs. And this is a very this is the large subject with very long history. On the other hand, it also connected to many other subjects like 2D CFTs, quantum groups, and quantum computations. MTCs are nice in many different ways. One thing that make it very nice to study is it's rigid. This is known by the name Ocneano rigidity. Basically, it does not have any continuous parameters. The space of MTCs are discrete. And furthermore, it's finite. At any given rank, you only have finitely many MTCs. This is proven in this paper. So all of this is just trying to encourage us to set up a classification program, rank by rank. Because if we want to understand what are the possible 3D gap physics, we need to understand what are the possible MTCs. So it's very simple. It's basically two steps. First step, you write down all the fusion rings at each rank. And the second step, for each fusion ring, you try to solve the consistent relations, known as pentagon and hexagon relations. So they are just given by they just specify the isomorphism between different maneuvers. We don't need the actual definitions, but those consistent relations are notoriously hard to solve. So they are all cubic in R and F, and there are a lot of equations. If you just stare at them, you can easily count there are many more equations than variables. The solutions do not always exist, and it's very hard to find like given solutions, like given rank, to find a solution to those large number of equations. And in case you haven't tried, even the first step is already very hard, because you need to find the commutative associative algebra, right? And there are a large number of choices. So just try to do this classification is actually very hard. As a result, we actually know very little about the space of MTCs. Here is a very incomplete timeline, but just to give you an idea, the effort people put in order to try to classify MTCs. So very recently, there was a paper, 2023, that pushed this classification program to rank 11. But to my knowledge, lots of the MTC they found, the F and R symbol are not known yet. So in those two last papers, they only determine the modular data, S and T, not an F and R, which is an extra difficulty task. So what could our project buy us in understanding the MTCs?
Very quick question.
Yeah, sure.
So are they sure that this MTCs exist then?
No, because so you are seeing the last two steps,
Right.
last two
Because they
papers?
don't know
Yeah,
FNR symbols.
exactly. Yes. So so roughly speaking, they haven't checked all the possible consistent relations. They solve part of the equations, and it's a final list. So all the possible MTCs should be contained in their list up to rank 11. But I guess, yeah, it's not guaranteed all the solutions they found will give you a well-defined MTC.
Okay, thanks.
No problem. So if the proposal we propose is gonna work, it teaches us many things about MTCs. For example, it tells us many MTCs, maybe a large chunk, maybe it's not crazy to say maybe all of them, actually characterized by 3D geometries together with the choice of group. And we try to put this simple crazy idea to test, and it turns out up to until rank 5, all of the MTCs, including non-unitary ones, can be constructed this way, just by changing M3 and our group here. And in the whole process, this mysterious product play an important role. It turns out many MTCs, it doesn't look like a factored thing, but it turns out it's the a graded product of this category, this individual factor I was describing. And more importantly, this category I was denoting C, PQ. This category is relatively well understood. A lot is known about them, S matrix, T matrix, and I believe many of them, for many of them, F and R are also known. So if you have a new MTC that's known to be constructed this way, and you already know what are F and R, just because this is understood. So this this whole proposal gives you a very simple way to compute F and R symbols.
Sorry, another question. Do you have control on whether, given a choice of M3 and group, you get a unitary or non-unitary MTC, or is something that you have to check a posteriori?
Yeah, that's a very good question. At the moment, I don't know a priori. Yeah, I have to check after I figure it out. Like,
but are there like maybe we'll discuss, but are there like similarly looking pairs of M3 and the group, which gives one gives a unitary, one no unitary, or you see some pattern?
Right. At this moment, I don't know if there are any simple pattern.
Okay.
Hi, sorry, excuse me.
Yeah.
Can you hear me?
Yeah.
Thanks.
Go ahead.
Can you remind me the condition for a non-unitary MTC? What's the difference? What's the condition difference? Thanks.
The simplest way to check whether a MTC is unitary or not is just look at the scaling so the quantum dimensions. The unitary MTCs must have all the quantum dimensions bigger than 1.
Yeah, thanks.
Bigger or equal to 1. Yeah.
But they are still real, even for non-unitary.
Yes.
Okay, real number. But,
yeah, they could be negative, for example.
They could be negative and also can be smaller than 1.
Yeah, exactly.
Okay, thanks. But what's the condition that makes a difference? Like, are there some criteria not satisfied for non-unitary MTC, but need to satisfy by MTC? I mean, this quantum dimension is a nice one, but is there some formula, certain formula like restriction form?
What
Just like your pentagon equations earlier, are there certain criteria that have a criteria? That's what I mean. I like this
see.
quantum dimension. That's good. That's good enough. But just in case you know which condition or also constraint obeyed by unitary MTC, but not obeyed by non-unitary MTC.
I guess a much harder thing to check is to require the F and R to be unitary.
Okay.
Yeah, but they are not gauge invariant, so it's a much harder thing to check.
Okay. So you're trying to say that perhaps the F symbol that switch between the basis of the fusion space, perhaps the sum of this amplitude, the square, doesn't equal to 1, for example, that type of condition.
Yeah.
Yeah, I cannot recall, but thanks. I'll double check.
Yeah.
Thank you.
Yeah. Cool. Thanks for the question. So this is about MTCs. On the other side, we can actually learn something new about the topology side. So the thing we are interested in is flat connections on this space. So mathematically, the flat connection is basically a map, a homomorphism from a fundamental group to the group GC. I'm only interested in SLNC here in this case, up to conjugation. And a particular type of flat connection that's interesting is called irreducible. That's the one that has a discrete stabilizer group. So roughly speaking, a very easy way to understand this irreducible condition is that I want the image of my rho to be spread out inside GC. I don't want all the image of my fundamental group when I apply rho to it is like SL2 or U1 subgroup of GC. It's like in that case it will be like classifying as SL2 flat connection. So I want to study irreducible flat connections. So this is a very important piece of knowledge we need in physics. For example, if you do compactifications from higher dimensional quantum field theory down to lower dimensional one, you need to understand, especially when you do gauge theory compactification, you need to understand what are the space of flat connections. And for Seifert manifolds, very little is known. It's only the simplest case where you have SL2C and 3 fibers. So like P1 over Q1, P2 over Q2, and P3 over Q3. It's only this one is known. And if you generalize to higher rank, SLNC, and all more fibers, and pretty much nothing is known. So what we learned from our project is the following. Actually, part of the answer to the question, what are the irreducible flat connections, are actually very simple. So this part is what we call anionic flat connections. I will give you the detailed definition later. But it's this part of the flat connections is the one that map to anions in the MTC side. So we can use the knowledge of our MTCs to say what are the space of flat connections. Of course, we're also interested in non-anionic ones, but that's the part that's work in progress. So that's about the motivation and background. I'm going to move into the details of the correspondence if you have any questions. So in order to understand this correspondence, we need to look at the flat connections and how to solve them seriously. So this is a Seifert manifold, and the fundamental group is known. So it's just described by n+1 generators. So I have n of them called X, and an additional one called H. So, and it's subject to 3 types of relations. The first one is H has to be central. That means it has to commute with everything else. And the second one is the product of S is 1. And lastly, for each fiber, so K equals to 1 to N, for each fiber, you need to require the X to some power and H to some power equals to 1. So those are the equations you need to solve. And to say I'm interested in a flat connection, that means I want to solve this set of equations using SLNC matrices. I want to find set of matrices that solve these equations. So let's try to break it down into small steps and see how far we can push along this direction. So the first step is we are interested in irreducible flat connections. Sorry. And together with the fact that H is central, you can easily see that this image of H has to be proportional to identity matrix. It's an identity matrix in the SLNC. And we also need the rho of H is SLNC. So it has determinant 1. That means the coefficient has to be a root of unity. And there are n choices for SLN. And for each choice of H, we can solve for xi's. Right? So we already know the space of flat connections is going to be decomposed into n disjoint sectors. This is the one that corresponds to the Zn gradient on the MTC side, that corresponds to the Zn one-form symmetry. And in each sector labeled by L, so L is a choice of Zn, we can try to solve the rest of the equations. For example, let's look at this equation. This is also very simple to solve. If you look at eigenvalues, this is basically saying this matrix to some power is proportional to, so remember this guy is proportional to identity. So they're saying the X to some power is proportional to identity. So the eigenvalue has to be root of unity too. So let's try to look at so I call the eigenvalues A, and because the determinant of this matrix rho X has to be 1, this trace has to be 0. And now to the p power is 1, that means each of them is just root of unity. This factor is just needed to make sure I get the correct factor, because H is not identity, it's proportional to identity. And each mu here is just an integer. So that means this rho of H is actually not the possible choice of eigenvalues is not continuous. It's just discrete subset. We also need 2 other constraints, right? So first one is the whole thing is promoted by while group, right? I don't care about the order of the eigenvalues. So I need to be quotient out by this while group Sn. The second thing we need is we make an arbitrary choice here, but A and A+1 is identified. So that means we need to those are the gauge choices that we need to take into account. If you do that, what you get is actually a finite set of possibilities within a complex region. So I will call that region R, that's labeled by P, Q, N, and L. So here I am giving an example for n equals to 3. So this is n equals 3, and this is rho of X is e to the 2 pi I, and then A1, A2, and A3. Because some of them, is 0. I'm just plotting A1 versus A2 here. It's discrete because it's root of unity, and it's a complex region instead of infinite region because of this two gauge I need to impose. Okay, now we have this. Right? Here is the definition of anionic. So I want to make a simplifying assumption that I'm only interested in the ones that are inside here, that are inside this complex region. On the boundary, I would call them non-anionic. Just as the name suggests, it's the inside that's gonna give me the anions on the other side of correspondence. So here I'm doing analysis for a single fiber, right? I'm solving the equation x to the power of p, h to the power of q is 1. Now I use the notation, this ring here at the top to denote the interior of this region. And the same way to say this is I don't want the eigenvalues to be the same. So if you have any two eigenvalues are actually the same, then you go to the boundary of this region. So now let's try to summarize what we have so far. So for each fiber, P1 over Q1, we try to solve two equations. H is central, x to the p, and h to the q is 1. And we get this interior of the region. And for the next fiber, we have this, and we solve another region, right? But h is shared for different x's. That means we need to, for each L sector, we need to solve different fibers together. And when you tensor product them together and then sum of them. You can see already from here, this is exactly the same as the graded product, graded Deligne product I was describing earlier, right? So if I have like C equals to sum over G over A, CG, right? And C A is the same as CG, DG, sum over A. Okay. So what's the rest of the equation we need to solve? This is one. This is the hardest one because it's highly nonlinear. The second equation we need to solve is we need to make sure the flat connection is irreducible. So the stabilizer has to be finite. So now you can put this into a computer. You can parameterize this this matrix U, because we know what is the D here already. We parameterize U and put it into a computer and try to solve this numerically. It's still very hard because the matrix can be very large and there are many fibers. But in simple cases, you can do it. So now the natural question is, among this possible set, right? Each point in the set give us a possible candidate of eigenvalues, and among the set, which one solve these two conditions, aka that give us the valid irreducible flat connections. So let me tell you our conjecture. This is a conjecture that supported by a large number of numerical texts. So the conjecture is basically any point in this region give us a valid irreducible flat connections. But it's not the case if you include the boundary. So if you include the boundary, then it's not true anymore. If you only consider the interior, then then any point inside the interior will give us an irreducible flat connection. And what's more interesting is the follows. So each region that looks like this this triangle here is actually the same as the F and Y curve for F and Lie algebra for SLN with level P minus N. So there's a way to map each point inside my region, which, as I recall, this is the one that give you eigenvalues. Each point give you a point that in the F and Y curve, which is a weight. And this is the formula. Okay. So that means we have the following a very natural isomorphism between the two following things. On the one side, we try to solve flat connections. We are interested in anionic ones that's inside, that's in interior of this region. And for each sector L, that's the H that's proportional to e to the 2 pi I L over N, proportional identity. You try to solve this. And for each point in this sector, we find a flat connection. But the whole problem is the same as this MTC, because each anion, just like chain summons, is also labeled by a weight inside this F and Y curve. And if you compare this part, this is precisely the reason we need this Zn. It's precisely because we need to solve the flat connections for each sector L.
May I ask a question?
Yeah.
So the graded product is always graded itself. So the MTC will always have a Zn one-form symmetry, right?
Yes.
If you want an MTC without one-form symmetry, the construction doesn't work, or what do you do?
One way to do this is to include a right. That's a very good question. So suppose you have this, right? But I don't require this. Like each component. Sorry. I'm not requiring every single component to be a non-trivial. So you can, if D has a one-form symmetry, but C does not, then what you get is basically C0 times D0.
I see. Okay.
Sorry. Does it mean that basically you are considering anion condensation also?
Why?
Say you start from some MTC with all components and then you forget some of them. Could it be interpreted as you start from an MTC with a Zn one-form symmetry and then you condense it, or condensing subgroups?
Yes, it's very yes. Basically, that's the one way to incorporate. Right, exactly. So that's one way to incorporate. So one way to understand this is just doing chain summons for each individual factor. And suppose you want to only look at one component of the chain summon theory, you just try to tensor it. You use this tensor product. The tensor is the one with no one-form symmetry. Yes, that's exactly right. But the only thing you have to make sure is the resulting category is modular. That's the only thing you have to be careful about. But otherwise, you are completely right.
Sorry,
Sorry,
is the abelian one-form symmetry anomaly-free? Guaranteed to be anomaly-free, or?
No, I don't require that.
So we cannot understand it as a gauging.
Right.
I mean anion condensation.
Yes. So it's not exactly the same as anion condensation in that sense. Yes.
Okay.
But it's similar in the sense that it projects to the zero charge sector.
Does the anomaly have a geometric meaning?
That's a very good question.
You can get it, right, from because the B cup B anomaly, right? You can get it from reducing this putative 60 theory that we haven't really talked about on the
Yes.
on this M3, and then that will generate exactly this coupling.
Yes. So there's a speculative relation to 3D correspondence of this whole setup, and if you use that, then yes, actually you can find out the anomaly from dimension reduction from 60. All right. So so now now I have basically tell you how the objects are mapped to each other between the geometry side and MTC side. And the take-home message is basically, although it's not obvious, but it turns out the simple objects are naturally labeled by the same set of weight in the weight diagram, in the weight lattice. So what are the things we need to check? So one of the first thing you need to make sure is if I give you two manifolds and they are diffeomorphic, and you better hope for you get the same MTC back, right? And so one of the so for example, the diffeomorphism can be understood in this way. Suppose you have two geometry M3 and M3 prime, and you this is a typo, and you change the Q in some way such that this equation is satisfied. Then this two geometry is known to be diffeomorphic. We don't have a full proof, but of all the meanings of cases we've checked, this is the case that the MTC you get for these two geometries are exactly the same. Okay, that's nice. The second check we can do is, well, this is more of a lesson from the correspondence than a check. So one of the conditions you have to be careful about is, we are looking for MTCs, not just any pre-modular categories. So if you take the product of two MTCs, it's not guaranteed to be MTC again. For example, there are some simple exercise you can do. Suppose you take two SU2 level K, and you ask, when does it become modular again? And it turns out it's modular if and only if K1 plus K2 is even. Okay, and if you try to do this for the one with 3 factors, and you get the following equation. It seems pretty random. And if you're increasing the number of factors, you multiply it by something, or you increase the rank here. Then it's very hard to recognize what is the equation you need to solve in order for the resulting category to be modular again. But it turns out all of this can be summarized by one sentence, that MTC is modular if and only if the first homology group of the M3 with Zn coefficient is trivial. In the simplest case where you have SU2 and 3 fibers, this was proved analytically in this very nice paper here. Using our proposal, we've checked up to, I think, n equals to 5 at least, and small n equals to 6. This is still true. So now it's just very hard to overlook the fact that the geometry tells us something about this MTC. So one more thing that I like to mention about these two relations is how do I match the topological invariant between two sides? So this is not fully developed because there are so many topological invariants we need to match. The simplest one we can do is the classical Chern-Simons invariant. So I was describing the flat connections in using the math language, right? So pi1 from M3 to SL and C. But a simpler way to understand the flat connections is simply using the gauge field. And if you use that, you can calculate the Chern-Simons function integrated over this choice of M3 you defined. For Seifert manifold and SUN gauge group, this has been computed by Nishi back in 1998. It has this form. I don't expect you to read this formula. And just make sure it's known, and it has a very close form formula. This was suggested that this topological invariant should be mapped to the spin. So the spin, this is the T matrix is e to the 2 pi I C 24, and then this is theta. I can also understand this as the e to the 2 pi I H, where H is the spin of a primary. And it's not obvious because if you look at the formula, this has S and R, but our twist does not have that. And we also have an L in each sector, but this one does not. So, but it turns out it worked. That because of some number theory miracle, these two formulas are exactly matched to each other. Okay. Any questions?
Just a clarification, because at some point I was a bit lost, because at the beginning you started talking about general groups, then you focused a lot on SLN. So can you change it, right?
Yes.
So you're focusing on the E series, but in principle you could choose either D or E, right?
Exactly. Yes.
And so if you start from say that you know that your starting MTC is the one generated by some Chern-Simons theory with some gauge group G and some level, can you obtain what is the corresponding Seifert manifold and the corresponding group?
For Chern-Simons, pretty much yes, because of the discussion we had earlier. So suppose you have let's see, you have some MTC1 product of MTC2, and then product MTC3, right? And we want this to be a Chern-Simons. One simple way to do this is you choose a simple MTC such that suppose I don't know, this one has Zn one-form symmetry, right? So you choose a simple one such that in each greedy component you only have one anion. This one. And this one is your Chern-Simons. Such that like you have a C, D, E, right? You have a C, G, D, G, E, G, and you sum over G, you get your final MTC back. You just want to make sure every CG and DG are you only have a single object in those components. Then in the resulting one, just give you the one you want. And we know how to find Chern-Simons because that's basically my category GP1. I choose my Q to be 1 here. That's just a Chern-Simons.
But what if you start from a Chern-Simons with a gauge group which is not simply lazy?
Right. Yes, that's a great question. In that case, I don't know.
Okay.
Yeah.
So
But
So
we
you're
had
proposing
one
that
example, right, where we needed to use a C type.
Yeah,
to
yeah.
actually
I
find the-
I guess Andrea was asking, is there a simple way to see what is the geometry corresponding to a transformers with non-simplest list?
that's right.
In that
some
case, we
kind
don't
of
know.
identical
Yeah.
thing.
Yeah,
Uh-huh.
because the reason for that is why it's not obvious is because you don't have such simple choice anymore. You are not such simple choice is not available. You don't have
Basically,
yeah.
If I understand correctly, if you start from a Chern-Simons with a simply laced gauge group, you will end up with some Seifert manifold and an associated group which corresponds to the group you started with, right?
Yes.
But if your original group is not simply laced, then you will end up with some other Seifert manifold and a group which is simply laced. Because you are proposing that all MTCs should be classified by Seifert manifold and simply laced gauge groups, right?
But it could come from something you didn't expect. I like, for example, if you ask me what is Ising, I don't have a simple way to tell you which Seifert manifold give you Ising, except doing calculations.
Right, but I mean, in the
yeah.
in the early days of Chern-Simons theory, Moore and Seiberg had this conjecture that all MTCs come from some Chern-Simons theory with some level. Now, as far as I understand this conjecture to be true, you have to include anion condensation at least. But still, it is at least possible, I think, that you can generate all MTCs starting from some Chern-Simons and including anion condensation. So in principle, you could map this to a problem in Chern-Simons theory. And if you start from some Chern-Simons with non-simply laced gauge group, it seems you're ending up again with a simply laced gauge group which classify the MTC.
No, I'm not sure. I'm not sure why. I could have chosen this G to be non-simply list. That's okay. I can do
okay,
that.
okay.
Yeah. This is why, like, I'm not talking about 3D correspondence. I guess, you know, if you are coming from 6D, and it's hard to imagine you are studying a non-simply list gauge group. But I'm not doing that.
Okay.
Yeah,
I understand. Thanks.
In principle, G can be anything.
I see. Okay.
Yeah.
Okay.
And in fact, in our paper, we do have some examples. I was restricting to SLNC because it's simple. Formulas are a lot simpler.
No, I was just confused that I thought that the claim was valid only for simply laced gauge group, but okay, no.
No. Just to continue that, you raised a very interesting point. So our proposal is like a more upgraded version of that conjecture, in the sense that we also allow this weird graded product of Chern-Simons theory. So if you think of this, like, I want to emphasize this individual factor is not Chern-Simons, but it's very close to Chern-Simons. But now I don't just have this, or it's anion condensation of it. I also allow myself to have this product of those individual factors. This gives us a lot more freedom to construct new MTCs. Okay, thank you for the questions. So let me summarize what I've said so far. So I'm trying to convince you that there is an interesting correspondence between MTC and Seifert geometries, together with a choice of a complexified gauge group. And you can easily infer many powerful new theorems from this if the correspondence is correct. For example, on the characterology side, this is basically in the space of flat connections. Little was known about this space, but now we know, at least interior of the so-called anionic flat connections are just given by anions on the MTC side. And we pretty much know everything about this, is this MTC, right? Like everything can be computed. This C blah blah C. So we now know what does this character variety for any number of fibers, any gauge group look like. And on the MTC side, this gives us a new way to construct MTCs. And most of the knowledge is given to us by this gridded product. It's using the familiar object, CGPQ, to construct MTCs. And I think it strongly hints some hidden structure in the space of MTCs that we didn't know before. Instead of just trying to scale up your algorithm, you use supercomputer to classify MTC to solve the FNR equations. Maybe we need to look for like what are the structures inside the space of MTCs we can utilize. But at this moment, this is still like an initial phase of the project. We have so many open questions we don't know. Some of them were already mentioned. For example, the numerics we have done is mostly for SLNC. It would be very interesting to look at other gauge group, the non-simply list ones, and maybe the PSLNC. That would teach us what happens if you change the global structure of the gauge group. What if you include a higher genus? At the moment, we are only looking at G equals 0. But most of the structure, if you look at pi 1 of M3, most of the structures are still there. So I guess you can have a similar proposal with minimal modifications. Another very important question is to what extent this is the correspondence between two categories. Right? There's a lot of data inside the category. For example, F and R symbols. We don't know what's the image of FR symbols inside the geometry. Another thing would be very nice to figure out is, there are many, like people understand a lot about 3D topologies. You can do all sorts of cutting and gluing techniques and to construct new geometries. And I don't know what happens on the MTC side. If you have M3 and you do some kind of operation and you have another M3, MTC, what is it in terms of MTC M3 and MTC M3 prime? And lastly, the original paper was studying 3D correspondence. They had a similar proposal, so our proposal is different even in the case of SL2C and n equals to 3. And the original proposal is not generalizable to higher rank or higher fibers. But I do wonder what happens, like what teaches us about 3D correspondence, because the whole construction, is so reminiscent of the 3D correspondence, where you have a 3D theory on one side and the 3D topology on the other side. And lastly, it was already mentioned, in physics, we ultimately are more interested in unitary MTCs. And the current form is quite hard for me to figure out what is unitary, what is not, just by looking at P over Q, like by looking at the geometry data. I have to, in order to figure out the MTC is unitary or not, I have to map to the MTC side and look at the S matrix, figure out the quantum dimension and so on. And it's a lot of computation we might need to do. It would be nice to understand, to narrow down the possible M3 on the geometry side, to figure out what are the UMTCs we are eventually interested in. Okay. With that, let me thank you for all the questions and thank you for listening.
So thank you, Jingxiang. It was a very nice talk. Are there any questions? I believe Juven had a question and there was another question in the chat.
Right. Yeah, I can say something about non-semi-simple. So we don't have a full picture yet, but the non-anionic part. So I was so here, right? So we're only looking at the interior of this region, because the boundary of this region is harder, and the proposal is they correspond to non-semi-simple MTCs.
There's also a question by Juven if you scroll up in the chat.
Earlier was your comment in that the quantum dimension can be negative, but I wonder whether I'm remember something not correct. I saw quantum dimension is constrained by 1 over some F symbol absolute value, so which probably will be larger than 0. So do you get quantum dimension smaller than 0 for non-unitary MTC?
Yes, I'm not sure. Yeah, I agree. There's a formula from F symbol, but I don't recall the precise form. But I believe it can be negative.
Okay. Thanks.
Looks like there are no more questions.
Sorry, I have another question. I'm trying to interpret this correspondence, like, say, physically, to understand also whether one can derive it, because basically you are proposing that every anion is given by some flat connection with some condition, right?
Yes.
But then this is also reminiscent of the fact that say if you take Chern-Simons theory with a gauge group, then you may try to define anions by, say you fix a link, then you do surgery on this link, you go to some manifold, then you can try to define the anion as a disordered operator by performing the path integral on some singular connections. So maybe this could be related with what you're saying, that the flat connection that you are assigning is the one that defines for you the anion as disorder defect. Can this be true, or have you thought about this?
I haven't tried that. Right. Yeah, that's a good point. I don't know. But that requires me to study the SLNC, this complex Chern-Simons, though. That's the complexity you need to deal with. But other than that, I think, yeah, that one should look into that.
Any other question? Okay, so let's thank Jingxiang again and stop the recording.